Tonight, we're going to do something that every piece of science education about the solar system neglects to do properly. We're going to tell you what would actually happen to your body if you were standing on each of the planets, moons, and major objects in our cosmic neighborhood. Not in the vague, comfortable language of, it would be very cold, or the pressure is extreme. In the specific physical, biological language of exactly how long you would survive, what would kill you first, and how quickly it would happen. The solar system contains 8 planets, dozens of major moons, millions of asteroids, and hundreds of dwarf planets. Almost every one of them would kill an unprotected human being in a time frame ranging from fractions of a second to a few hours, with a handful of outliers that might allow survival measured in minutes. The exceptions to instant death are rarer than most people would guess, and even the most survivable locations in the solar system outside Earth would still kill you within a day through one mechanism or another. Understanding what kills you on each world and how fast is not morbid for its own sake. It is the most efficient way to understand the specific physical conditions of each location in the solar system, because the killing mechanisms are precisely the physical properties that make each world what it is. The temperature on Venus is not just a number in a textbook. It is the reason you would be simultaneously crushed and dissolved. The wind speed on Neptune is not a curiosity. It is the reason you would be moving at 1,300 miles per hour within moments of arriving. The radiation at Io is not just an atmospheric science footnote. It is the reason your DNA would be unraveling within minutes. The scenario for tonight is simple and consistent. You are a normal, unprotected human being. No spacesuit, no protective equipment of any kind. You are transported instantaneously to the surface of each object at a representative location, and we examine what happens next. We will ignore the question of how you got there, because the physics of arrival is a separate problem from the physics of the environment itself. We are interested in the environment. The question is always the same. How long before you die? And what kills you? The answers will tell you more about the solar system than most textbooks manage to convey, because survival time is a direct function of how far a place's conditions deviate from what a human body can tolerate. And those deviations map precisely onto the most important physical characteristics of each world. By the end of tonight, you will have a working intuition for the hierarchy of hostility that characterizes the solar system, a sense of which worlds are merely brutal and which are instantly fatal, and a deep appreciation for the extraordinary improbability of the one world in this entire neighborhood where you could survive at all without any equipment whatsoever. If this kind of specific, real, consequence-grounded tour through the solar system is what you want, subscribe and leave a like. It helps this channel reach more people who want the honest version of what these worlds are actually like. Now, let's start with what a human body can tolerate, so we have a baseline for everything that follows. There is an important clarification about what we mean by survival time in this context. We are not asking how long you could survive if you had some equipment, or if you were somehow adapted to alien conditions, or if you held your breath at the right moment. We are asking about the unadorned, unprotected human body in each environment exactly as it is, and we are counting from the moment of arrival to the moment of biological death. The comparison is honest and unsparing, and it will require that we be specific about what kills you in each case rather than vague about the severity. The solar system we will tour contains the Sun at the center, 8 planets ranging from rocky inner worlds to gas and ice giants, and a collection of moons, dwarf planets, and other objects. We will visit the most significant of these in sequence, moving from the inner solar system outward before ending with the Sun itself. This ordering is deliberate. It allows us to build an intuitive map of how survivability changes with distance from the Sun and with the type of object being considered. The pattern that emerges will be surprising in some respects and deeply illuminating in others. The scenario requires no spaceship, no deceleration, No transition period. You simply appear, and the environment immediately does what it does. This is somewhat fantastical as a scenario, but it is the cleanest way to isolate the environmental conditions from the complications of travel. We want to know about the places, not about the journey. Before standing anywhere in the solar system, it is worth establishing precisely what your body can and cannot handle, because the killing mechanisms on different worlds exploit different vulnerabilities. The human body is an extraordinarily delicate system that operates within very narrow ranges of temperature, pressure, atmospheric composition, and radiation dose. Push any of these parameters significantly outside their acceptable range, and biological systems begin to fail quickly and catastrophically. Temperature is the most familiar killer. The human body maintains an internal core temperature of approximately 37 degrees Celsius, and it has impressive but limited ability to regulate this temperature in the face of external extremes. In extreme cold, the body conserves heat by reducing blood flow to extremities, which eventually causes frostbite and tissue death in the fingers, toes, nose, and ears. As core temperature drops below 35 degrees Celsius, hypothermia sets in. The heart rhythm becomes irregular. Cognitive function deteriorates, and eventually the heart stops. Full cardiac arrest typically occurs when core temperature falls below 28 to 30 degrees Celsius. In extreme heat, the body sweats to shed heat, but sweating requires water and can only cope with a limited rate of heat input. Above roughly 42 degrees Celsius in core temperature, enzymes begin to denature, brain function deteriorates, and death follows within hours to minutes, depending on the severity. Dry heat of 50 or 60 degrees Celsius ambient temperature is survivable for hours if the body can sweat and the sweat can evaporate. Ambient temperatures above about 180 degrees Celsius for extended periods overwhelm all compensating mechanisms instantly. Pressure is a more complex killer. The human body can survive atmospheric pressures ranging from roughly 0.3 atmospheres, approximately the pressure at high-altitude mountain peaks, to about 10 atmospheres with appropriate gas mixtures. Below 0.063 atmospheres, the boiling point of water at body temperature means that bodily fluids begin to vaporize. This is called ebullition, and it is distinctly unpleasant. Dissolved gases come out of solution in the blood and tissues. The skin and soft tissues swell dramatically, and the lungs cannot absorb any oxygen from an atmosphere so thin. Loss of consciousness occurs within about 15 seconds at near vacuum, and death within a few minutes. At the other extreme, high pressure with the wrong gas mixture causes nitrogen narcosis, oxygen toxicity, and eventually pressure itself compresses the lungs and other gas-filled cavities lethally. Atmospheric composition determines whether you can breathe at all. Your body requires oxygen at a partial pressure of roughly 0.16 to 1.6 atmospheres. Below 0.1 atmospheres of oxygen, partial pressure, unconsciousness follows within seconds. Carbon dioxide above 5% of atmospheric composition causes hypercapnia, which rapidly produces unconsciousness and death. Many of the atmospheres we will encounter contain no oxygen at all, or contain gases that are directly toxic. Venus has an atmosphere of carbon dioxide and sulfuric acid vapor. Titan has nitrogen and methane. Jupiter has hydrogen, helium, ammonia, and methane. None of these support respiration. Radiation is the final major killer in the solar system. Human cells can repair moderate radiation damage, but above a whole body dose of about 3 to 5 gray, radiation sickness becomes life-threatening. Above 10 gray, death within days is essentially certain. Above 50 gray, death within hours. The radiation environments near Jupiter's moon, Io, at the surface of Mars without a magnetosphere, and near any unshielded radioactive material can deliver lethal doses in minutes to hours. With these parameters established, we can now evaluate each world systematically. It is worth adding one more biological parameter that will come up repeatedly: the effect of acceleration and gravity on the human body. The human body is adapted to function under Earth's gravitational acceleration of approximately 9.8 meters per second squared. Under higher gravity, the cardiovascular system must work harder to pump blood to the brain against increased gravitational force. At about 5g sustained acceleration, the blood drains from the brain, and unconsciousness follows within seconds, even for trained fighter pilots in pressurized flight suits. At higher sustained gravitation, organ damage from the weight of body tissues pressing against each other would follow rapidly. Under low gravity, the opposite problems occur over time. Fluid redistributes toward the head, causing facial puffing and impaired vision. Bones lose density without the mechanical loading that normally maintains them. Muscles atrophy. These low-gravity effects are not immediately lethal and would not be relevant in our short-term survival scenario, but they are worth noting as a longer-term consideration for worlds with very low surface gravity. The critical point for our exercise is that humans have no ability to adapt to any of these environmental parameters on a timescale of seconds to minutes. Biological adaptation requires generations. Physiological acclimatization requires days to weeks for parameters like altitude adjustment, and months for parameters like cold adaptation. In the time frame of our scenario, every individual represents the same baseline human body with the same tolerance ranges, and those ranges are fixed. Mercury is the innermost planet and has a surface that presents a specific and extreme challenge that is different from what most people expect. The common assumption is that Mercury is simply very hot because it is close to the Sun. The reality is more complicated and in some ways more interesting. Mercury has no meaningful atmosphere, almost none at all, just a trace exosphere of atoms sputtered off the surface by the solar wind. This absence of atmosphere means that temperature is determined entirely by the balance between solar radiation and radiative cooling, with no convection, no weather, and no thermal buffering of any kind. On the sunlit side of Mercury, the surface temperature reaches approximately 430 degrees Celsius, hot enough to melt lead. You would die from thermal radiation within seconds, possibly within a fraction of a second, depending on your exact position relative to the solar disk. The Sun from Mercury's surface appears about 2.5 to 3.5 times larger in angular diameter than it does from Earth. Because Mercury orbits between 46 million and 70 million kilometers from the Sun, compared to Earth's average of 150 million. The solar irradiance on Mercury's sunlit surface is between 4.5 and 10 times greater than on Earth. Standing unprotected in full sunlight on Mercury's surface, you would be receiving energy equivalent to standing less than 5 meters from an electric furnace in an industrial smelting plant. Your skin would begin to burn within the first second. Loss of consciousness would follow within a few seconds from the combination of extreme heat, vaporization of surface fluids, and cardiac stress. But Mercury also has a night side, and the night side tells a completely different story. Because Mercury rotates very slowly, completing one rotation every 59 Earth days, and because it has no atmosphere to distribute heat, the night side cools dramatically. Night side temperatures fall to approximately minus 180 degrees Celsius. At this temperature, if you were deposited on the night side, you would face the rapid onset of hypothermia rather than heat death. Your extremities would begin to suffer frostbite within seconds. Your core temperature would fall rapidly. Death from hypothermia would likely occur within 5 to 10 minutes, as core temperature plummeted through the lethal range. The immediate cause of death on the night side, however, would actually be the near vacuum before the cold had time to act. Mercury's surface pressure is approximately 10 to the minus 14 times Earth's atmospheric pressure, essentially zero. At that pressure, your blood and bodily fluids begin to boil at body temperature. You would lose consciousness within about 15 seconds and be dead within 2 to 3 minutes from embolism, even before the cold could complete the job. There is one location on Mercury that deserves special mention: the permanently shadowed craters near the poles. These craters, whose floors never see sunlight, maintain temperatures near -200 degrees Celsius and contain water ice that has been confirmed by radar observations. You would die from vacuum exposure in the same 15 seconds, regardless of the temperature. But the existence of stable water ice on Mercury is one of the solar system's more counterintuitive facts, and illustrates how the absence of atmospheric heat distribution can preserve extreme conditions over billions of years. Your survival time on Mercury: approximately 15 seconds on the night side from vacuum exposure, perhaps 2 to 5 seconds on the fully sunlit side before the thermal radiation incapacitates you, and then death within 2 to 3 minutes from embolism in either case. Mercury's lack of atmosphere has one additional consequence worth noting. There is no protection from micrometeoroid impacts. Earth's atmosphere burns up most incoming meteoroids through friction before they can reach the surface. The Moon has no atmosphere, and so every meteoroid strikes the surface directly, which is why the lunar surface is saturated with craters of all sizes down to microscopic pits. Mercury's surface shows the same cratered character for the same reason. While a micrometeoroid would not typically affect survival in our 15-second scenario, the background impact rate is a consideration for any long-term habitation, and illustrates yet another layer of the hostile environment that Earth's atmosphere shields us from. The longest Mercury day-night cycle creates extreme thermal challenges that go beyond the temperature extremes themselves. A solar day on Mercury, the time from one sunrise to the next on Mercury's surface, lasts approximately 176 Earth days. This means a location on Mercury's equator is in continuous sunlight for about 88 Earth days and then in continuous darkness for about 88 Earth days. The temperature swing between the day side and night side maximum from about 430 to -180 degrees Celsius represents one of the largest day-night temperature differences on any solid body in the solar system. Only the Moon comes close. For the same reason, no atmosphere to store and redistribute heat. The survival hierarchy on Mercury's surface, with sunlit sides killing almost instantly from heat and shaded sides taking several minutes to kill through cold, complicated by vacuum exposure, illustrates how the single factor of atmospheric absence creates multiple independent killing mechanisms on the same body. Venus is, without question, the most hostile planetary surface in the inner solar system for an unprotected human being. It is not the hottest planet in absolute terms, but it is the planet whose combination of extreme temperature, crushing pressure, toxic atmosphere, and corrosive chemistry creates the most comprehensively lethal environment conceivable. Every known mechanism of human death operates simultaneously and immediately on Venus's surface. The first problem is the temperature. Venus has an average surface temperature of approximately 465 degrees Celsius. Hot enough to melt lead, hot enough to melt zinc, hotter than a self-cleaning oven at maximum temperature. Venus is hotter than Mercury, despite being nearly twice as far from the Sun. Because Venus has an extremely thick atmosphere of carbon dioxide that produces an extreme greenhouse effect. The atmospheric pressure at Venus's surface is approximately 92 times Earth's sea level atmospheric pressure, equivalent to the pressure at a depth of about 900 meters in Earth's ocean. The temperature and pressure together create conditions more similar to a deep industrial furnace than anything in terrestrial experience. At 465 degrees Celsius, you would experience instantaneous and total thermal destruction of biological tissues. Water in your cells vaporizes almost immediately. Proteins denature within a fraction of a second. The organic chemistry that constitutes human life operates only within an extraordinarily narrow temperature range, and at 465 degrees Celsius, every biological molecule in your body undergoes irreversible chemical decomposition. For comparison, paper burns at approximately 232 degrees Celsius. The Maillard reaction that causes food to brown occurs around 140 to 165 degrees Celsius. At 465 degrees Celsius, you would not merely die, you would rapidly undergo something more analogous to combustion than to any biological process recognizable as death. The pressure would simultaneously be crushing your body with a force equivalent to diving to 900 meters in the ocean. At 92 atmospheres, every gas-filled cavity in your body, your lungs, your sinuses, your middle ears, would be compressed to a fraction of its normal volume in a fraction of a second. The lung compression alone would be fatal. Your rib cage would collapse inward. Your eardrums would burst, and your inner ear structures would be destroyed. The pressure differential would cause barotrauma throughout every tissue containing gas. The atmosphere itself is a third simultaneous killer. Venus's atmosphere is composed of about 96.5% carbon dioxide and 3.5% nitrogen, with trace amounts of sulfur dioxide and other toxic gases. In the upper atmosphere, clouds of sulfuric acid exist, though these are above the surface layer and would not be your immediate problem. The complete absence of oxygen means that even if the temperature and pressure allowed you to breathe, you would still have no breathable air. Carbon dioxide at high concentrations produces rapid onset of hypercapnia. The practical reality of Venus is that the three killing mechanisms, extreme heat, crushing pressure, and toxic suffocating atmosphere, all operate simultaneously, and all produce effects measured in milliseconds to seconds. You would be simultaneously being incinerated, crushed, and asphyxiated. The question of which mechanism kills you first is somewhat academic, since all three are operating in parallel. But the thermal effects would probably produce the most complete and rapid destruction of biological tissue. Your survival time on Venus, essentially zero, fractions of a second. You would be dead before you could register what was happening. The Soviet Venera probes, launched in the 1970s and early 1980s, provide the only direct measurements ever taken on Venus's surface. These robotic landers were designed specifically to survive the conditions, but even so, they lasted only between 23 minutes and 127 minutes before being destroyed by the heat and pressure. They were built from titanium and other heat-resistant materials with sophisticated thermal management systems and pressurized interiors. They were miniature submarines designed for an atmosphere equivalent to being 900 meters underwater in an oven. They lasted less than 2 hours. The longest surviving Venera landers transmitted data for 127 minutes. A human body, compared to a titanium pressure vessel with active cooling, would not survive a measurable fraction of that time. Venus's rotation is also notably unusual. Venus rotates extremely slowly and in the opposite direction from most planets, taking about 243 Earth days to complete one rotation, while orbiting the Sun in 225 days. This means a Venus day is longer than a Venus year. The combination of slow retrograde rotation and thick atmosphere means that the difference in temperature between Venus's day side and night side is almost non-existent. The atmosphere circulates heat so efficiently that the surface temperature varies by only about 10 degrees Celsius between the equator and poles and between day and night. There is no escape from the heat on Venus. Every point on the surface is approximately 465 degrees Celsius. The cloud decks of Venus, located at altitudes of 48 to 70 kilometers above the surface, contain significant concentrations of sulfuric acid droplets. These clouds are not directly relevant to surface survival, but they are one reason Venus reflects so much sunlight and appears so bright in Earth's sky. From below the clouds, the light reaching the surface is comparable to a heavily overcast day on Earth, despite the planet's proximity to the Sun. The Moon is the most familiar extraterrestrial object in human experience and the only body beyond Earth that human beings have walked on. 12 human beings stood on the lunar surface between 1969 and 1972, all of them enclosed in extraordinarily sophisticated life support systems. The question of how long an unprotected human would survive on the Moon illuminates why those suits were necessary and what the Moon's environment actually consists of. The Moon has essentially no atmosphere. Its surface pressure is approximately 10 to the minus 17 times Earth's atmospheric pressure, comparable to the vacuum of low Earth orbit, and for practical biological purposes indistinguishable from a perfect vacuum. This immediately means that the primary killer on the Moon is vacuum exposure, and it would act within the same 15-second timeline that applied to Mercury's night side. In a vacuum, the partial pressure of oxygen in your lungs falls to essentially zero. Oxygen stops diffusing from your alveoli into your blood. Your blood oxygen saturation drops rapidly. The brain, which requires continuous oxygen supply, loses consciousness within approximately 15 seconds of oxygen deprivation. After about 90 seconds without oxygen, permanent brain damage begins to occur. After 3 to 4 minutes, brain death is essentially complete, though the heart may continue beating for a few minutes longer. In the vacuum of space, your exposed skin and eyes experience additional problems. Saliva and the moisture in your nasal passages and throat would begin to evaporate and boil at body temperature, since the boiling point of water is approximately 37 degrees Celsius, at pressures comparable to what exists on the lunar surface. Your tongue would bubble. The moisture on your eyes would evaporate. These are uncomfortable and damaging, but not immediately the primary cause of death relative to the oxygen deprivation problem. Temperature on the Moon varies dramatically between the sunlit and shaded surfaces. The fully sunlit lunar surface in the equatorial region reaches approximately 127 degrees Celsius, hot enough to cause burns. The shaded side, or the surface at night, falls to approximately minus 173 degrees Celsius. However, these temperature extremes would not be immediately lethal in the same time frame as the vacuum exposure. In the time available, roughly 15 seconds of consciousness, the temperature effects on your skin would be secondary to the oxygen issue. What is sometimes described as explosive decompression, the idea that your body would explode in vacuum, is a myth. Human skin is strong enough to contain the body's internal pressure. You would swell somewhat as gases dissolved in your blood came out of solution, but you would not burst. The actual death mechanism is simpler. You stop being able to breathe and your brain stops receiving oxygen. Your survival time on the Moon, approximately 15 seconds of consciousness from vacuum exposure, followed by unconsciousness and death within 2 to 4 minutes, as oxygen deprivation produces irreversible brain damage. The Apollo astronauts were protected by spacesuits that are engineering marvels worth understanding in the context of what they were protecting against. The Apollo suits maintained a pressurized oxygen environment at about 0.35 atmospheres of pure oxygen, sufficient for breathing and for preventing embolism. They provided insulation against the extreme temperature swings of the lunar surface. They included a micrometeoroid protection layer. They carried life support systems for oxygen recycling and carbon dioxide removal. The suits were not merely clothing, they were miniature spacecraft, and the engineering challenge of designing them was immense. The fact that the Moon, our nearest neighbor, requires equipment of this sophistication for even a brief surface visit illustrates the dramatic difference between conditions on Earth and conditions everywhere else in the solar system. The Moon is approximately 384,400 kilometers away, close enough to reach in a few days, and yet its surface would kill an unprotected human faster than any weather event on Earth, except perhaps a direct lightning strike. One frequently cited fact about the Moon is that astronauts could see Earth from the surface. The psychological comfort of that visibility, of being able to see home, might seem to imply that safety was near. In reality, the Earth hanging in the lunar sky represents a location approximately 385,000 kilometers away where the conditions needed for survival existed. The distance between visual accessibility and physical accessibility was, for the unprotected human, effectively infinite. The myth of explosive decompression deserves direct refutation because it is so common in popular culture. In films, characters exposed to vacuum frequently explode, freeze instantly, or suffer other dramatic visible effects within the first second. The reality is far quieter, and in some ways more disturbing. The human body would swell slightly as gas came out of solution in blood and tissues, but skin is elastic and strong enough to contain this swelling. Moisture on exposed surfaces would evaporate. Blood pressure would eventually drop as the heart lost its ability to maintain circulation against the absence of external pressure. Death comes from oxygen deprivation, which requires no visible drama to be completely lethal. You would simply lose consciousness, as if falling asleep, and not wake up. Mars is the most survivable world in the solar system outside Earth, which sounds like a strong recommendation until you understand what survivable means in this context. Mars would still kill you, and it would kill you within minutes by multiple mechanisms. But those minutes represent far longer than any other planet or major moon would allow. Understanding why Mars is the survivable one illuminates what it would actually take to colonize it. The atmosphere of Mars is primarily carbon dioxide, at approximately 95.3%, with small amounts of nitrogen, argon, and trace gases. The total atmospheric pressure at Mars's surface varies with altitude and season, but averages about 600 to 700 pascals, which is less than 1% of Earth's sea level atmospheric pressure. This is far too thin to breathe and far below the threshold at which ebullition occurs, which is 6,262 pascals. Mars's atmospheric pressure sits just above the Armstrong limit, the pressure below which water boils at body temperature, but only barely. In the lowest elevations of Mars, like the Hellas Basin, pressure is slightly higher. On the highest elevations, like Olympus Mons, it is slightly lower and could be below the Armstrong limit during some conditions. If you were deposited on Mars without a suit, you would first experience the complete inability to breathe. The atmospheric composition contains essentially no oxygen, and even if it did, the partial pressure of any gas in a 0.006 atmosphere total pressure would be far too low to sustain respiration. You would begin to lose consciousness from oxygen deprivation within about 15 seconds, the same timeline as the Moon. This is the fastest acting killer on Mars. However, Mars does have an atmosphere, thin as it is, and this creates some differences from the Moon. You would experience some slight wind if there are atmospheric currents. The thin carbon dioxide would begin to enter your lungs, providing carbon dioxide poisoning on top of the oxygen deprivation, though this is secondary to the simple asphyxiation issue. The temperature on Mars averages about minus 60 degrees Celsius, with a range from about minus 125 degrees Celsius at the poles in winter to about 20 degrees Celsius on a warm summer afternoon near the equator. If deposited during a warm Martian afternoon, the temperature itself would not be immediately fatal in the 15 seconds of consciousness you have available. However, after unconsciousness from oxygen deprivation, the cold would continue to act on your body, dropping your core temperature and completing the process of death. Mars also exposes you to significant radiation. Without the magnetosphere that protects Earth or the dense atmosphere that absorbs cosmic rays and solar energetic particles, the surface of Mars receives radiation doses of about 0.2 millisieverts per day, roughly 700 times the average radiation dose on Earth's surface. This is not immediately lethal, but over weeks it would significantly increase cancer risk, and over months would deliver doses approaching limits for long-term habitation. The dust storms of Mars are another environmental consideration. Global dust storms can reduce visibility to near zero and cover the entire planet. They do not carry enough energy to sandblast equipment, as depicted in popular science fiction, but they do create enormous challenges for solar power and equipment maintenance. Your survival time on Mars? Approximately 15 seconds of consciousness before hypoxia takes hold, then unconsciousness, then death from oxygen deprivation within 2 to 4 minutes. The cold would continue to act after death, but the primary killing mechanism is the same as on the Moon: the absence of breathable air. The record of attempted Mars landings illustrates how difficult the environment is, even for robotic systems. Of approximately 50 attempted Mars missions as of the mid-2020s, roughly half have failed. The successes have included landers like Viking, Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance, each of which required extraordinarily careful engineering to survive the intense aerodynamic heating of entry, the thin atmosphere that makes parachutes less effective than on Earth, and the rocky surface that has ended some missions on landing. If robotic systems built specifically for Mars survival fail at this rate, the challenge of keeping humans alive there is orders of magnitude greater. The perchlorets in Mars's soil add another survival hazard to the already challenging environment. Perchlorate salts, which are toxic to humans primarily by interfering with thyroid function, are present in Mars's soil at concentrations of roughly 0.5 to 1%. Any dust that entered a habitat or a suit would carry these compounds, creating a chronic toxic exposure challenge. Combined with the intense ultraviolet radiation that breaks down perchlorate compounds in the soil into even more reactive species, the Martian surface soil is chemically hostile in ways beyond its obvious temperature and pressure problems. The positive side of Mars compared to all other candidates is that its resources are more accessible. The polar ice caps contain water ice mixed with carbon dioxide ice, and subsurface water ice has been detected at many locations. The thin atmosphere, while insufficient for breathing, is a source of carbon dioxide from which oxygen could in principle be extracted. The Mars Oxygen In Situ Resource Utilization experiment on the Perseverance rover has demonstrated that this extraction is technically feasible, producing small amounts of oxygen from atmospheric carbon dioxide using electricity. These resources make Mars the most plausible target for human settlement, despite its immediately lethal, unprotected environment. Ceres is the largest object in the asteroid belt between Mars and Jupiter, with a diameter of about 940 kilometers, making it a dwarf planet. It represents a category of object in the solar system that is often overlooked in surveys of this type, and what makes Ceres and similar objects interesting is that their killing mechanisms combine several problems simultaneously, while offering none of the dramatic extremes that characterize the large planets. Ceres' surface gravity is about 2.8% of Earth's, which means you could jump approximately 36 times higher than on Earth. While this is not immediately fatal, the extremely low gravity creates problems for long-term survival related to bone density loss and fluid redistribution in the body, though these would not act quickly enough to be relevant in our scenario of immediate unprotected exposure. The atmosphere of Ceres is extremely thin, comparable to or thinner than the lunar atmosphere. Observations by the Dawn spacecraft suggested that Ceres might have a very tenuous water vapor atmosphere produced by sublimation of ice in sunlit craters, but this is negligibly thin by any standard. For our purposes, Ceres is in vacuum, and the same 15-second oxygen deprivation timeline applies. Surface temperatures on Ceres range from approximately minus 105 degrees Celsius in the equatorial regions to about minus 180 degrees Celsius near the poles. These temperatures are well below the range that causes rapid frostbite, but again, they would not act quickly enough to matter given the 15-second consciousness window from oxygen deprivation. What makes Ceres particularly interesting from an astrobiological perspective, and what makes the asteroid belt interesting generally, is the evidence for water. Dawn detected bright spots in Octator crater that are deposits of sodium carbonate and magnesium sulfate, likely deposited by briny water that welled up from below the surface and evaporated. Ceres may have a liquid brine layer beneath its surface. This is relevant not to survival, but to the broader question of where in the solar system interesting chemistry might be happening. The asteroid belt generally is a cold, dark vacuum environment. If you were placed on a typical large asteroid, the specific gravity would determine whether you could even maintain contact with the surface. On a very small asteroid, your body's momentum from even the gentlest movement could exceed the escape velocity, sending you drifting off the surface and into space. On Ceres itself, the gravity is low but sufficient to keep you anchored. Your survival time on Ceres: 15 seconds of consciousness. Death within 2 to 4 minutes. Indistinguishable from the moon scenario, except for the somewhat lower gravity and even colder surface temperatures. The experience of navigating the asteroid belt is far less dramatic than science fiction suggests. The average distance between asteroids and the belt is enormous. If you were in a spacecraft traversing the asteroid belt, you would be unlikely to see a single asteroid with the naked eye. The Voyager and Pioneer probes crossed the asteroid belt without any protective measures because the probability of collision with any significant object was negligible. The asteroid belt is vast, and the total mass of all asteroids combined is less than 4% of the mass of the Moon. Despite this, very small particles and dust are more numerous than large asteroids, and the micrometeoroid impact risk over long periods is real for exposed surfaces. The surfaces of asteroid belt objects show evidence of space weathering. The gradual alteration of surface material by solar wind and micro-impact bombardment over millions to billions of years. These processes produce the characteristic dark, reddened surfaces of many carbonaceous asteroids. The scientific interest in asteroids extends beyond their role as a survival challenge. Carbonaceous chondrite asteroids, the most common type, contain amino acids, simple sugars, and other organic compounds that predate the solar system. They are time capsules from the early history of the solar system, preserving chemical information from the nebula from which the sun and planets formed. Sample return missions to asteroids, including JAXA's Hayabusa missions and NASA's OSIRIS-REx, have brought back asteroid material for laboratory analysis. The Ceres system is also of interest for its potential subsurface water, which makes it a target for future exploration. The visibility of space from the asteroid belt would be dramatically different from Earth's view. Without an atmosphere to scatter light, the stars would be perfectly sharp and the sky completely black even with the sun visible. The Milky Way would be a brilliant arch of stars across the sky, its structure visible in a way that Earth's atmospheric haze typically obscures. The Sun, from Ceres's average distance of 2.77 astronomical units, would appear smaller than from Earth, about 60 to 70% of its angular diameter as seen from Earth, but still blindingly bright against the absolute darkness. This view would be beautiful by any standard, and you would have precisely 15 seconds to appreciate it. Jupiter presents a fundamentally different type of survival problem from everything we have examined so far. The previous worlds all had solid surfaces, places where you could stand and face the consequences of the environment. Jupiter has no solid surface that a human could stand on. It is a gas giant, and the transition from the thin upper atmosphere to the crushing high-pressure layers of the deep interior is a continuous gradient with no firm boundary. If you were deposited at the cloud tops of Jupiter, you would immediately face the familiar problem of a non-breathable atmosphere. Jupiter's atmosphere is composed of approximately 89% hydrogen and 10% helium, with small amounts of methane, ammonia, water vapor, hydrogen sulfide, and other compounds. None of this supports respiration. You would lose consciousness within 15 seconds and die within minutes from oxygen deprivation, just as on the Moon or Mars. But the problem on Jupiter is that you would also be falling. The cloud tops are not a surface. They are a layer of gas, and below them is more gas, and below that, more gas at higher pressure and temperature. Jupiter's gravitational field at the cloud top level corresponds to a surface gravity of about 24.8 meters per second squared, roughly 2.5 times Earth's surface gravity. You would fall with 2.5 times normal gravitational acceleration. As you fell, the pressure would increase rapidly. Jupiter's atmosphere produces intense pressures at relatively shallow depths. Within tens of kilometers below the cloud tops, pressures reach tens of atmospheres. As you fell deeper, the atmosphere would become increasingly dense and hot. At depths where pressure reaches around 100 to 200 atmospheres, temperatures climb above 200 degrees Celsius. At greater depths still, the conditions approach the critical point of hydrogen, where the distinction between gas and liquid becomes meaningless. Eventually, at depths of thousands of kilometers, the pressure is so extreme that hydrogen behaves as a liquid metal, conducting electricity. Your body would be incinerated and crushed long before reaching the metallic hydrogen layer. The most dramatic aspect of death on Jupiter is the scale. You would be falling through an atmosphere larger than the entire volume of Earth, experiencing increasing pressure and temperature the entire way down, for as long as your body remains structurally intact. Jupiter also has an extraordinarily powerful radiation environment, driven by its massive magnetic field, which is about 14 times stronger than Earth's. The magnetosphere traps energetic charge particles and radiation, belts far more intense than Earth's Van Allen belts. Near Jupiter's cloud tops, radiation doses can reach hundreds of gray per day, orders of magnitude above lethal levels, though the oxygen deprivation would kill you faster than the radiation in this scenario. Your survival time on Jupiter, 15 seconds of consciousness while falling into the cloud tops, death within 2 to 4 minutes from oxygen deprivation, after which your body continues falling and is compressed and cooked into irrelevance over a period of hours as it descends into the deep atmosphere. The metaphor of Jupiter as a solar system in miniature is worth developing because Jupiter's system of moons, rings, and magnetosphere has structural similarities to the solar system itself. The 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, are roughly analogous to the inner planets in that they are much larger relative to Jupiter than most other moons are to their planets. And they show a gradient of properties with distance from Jupiter similar to the inner to outer planet gradient in the solar system. The innermost, Io, is the most geologically active. The next, Europa, has a liquid water ocean. The third, Ganymede, is the largest and has its own magnetic field. And the outermost, Callisto, is ancient and heavily cratered. The Great Red Spot, Jupiter's most iconic atmospheric feature, is an anticyclonic storm that has been continuously observed since at least 1831 and may have been seen earlier, making it a storm that has persisted for at least 2 centuries and possibly much longer. Its diameter was once estimated at 3 times Earth's diameter, though it has been shrinking in recent decades and is now about 1.3 times Earth's diameter. The winds at the edges of the Great Red Spot reach approximately 450 kilometers per hour. This is fast by terrestrial hurricane standards, though modest compared to the wind speeds we will encounter on Neptune. Jupiter's 4 large moons complete 1 to several orbits per Jupiter day depending on the moon, and from any point in Jupiter's atmosphere, these moons would be visible as dramatically large disks moving visibly across the sky on timescales of hours. Io, for example, subtends an angular diameter as seen from Jupiter's cloud tops of about 35 arc minutes, larger than the full moon appears from Earth. This is entirely irrelevant to your survival, but it is one of the more visually spectacular features of the Jovian environment. Io is Jupiter's innermost large moon and the most volcanically active body in the entire solar system. Its surface is covered with hundreds of active volcanoes, vast lava lakes, volcanic plumes that reach hundreds of kilometers into space, and sulfur compounds that paint the surface in spectacular shades of yellow, orange, red, and white. Io looks like a pizza, and it is about as hospitable as the inside of an oven. The volcanic activity on Io is driven by tidal forces. Io is caught in a gravitational tug-of-war between Jupiter and the other large moons Europa and Ganymede. Jupiter's massive gravity pulls Io strongly, while the orbital resonances with the other moons continually flex Io's interior, generating enormous amounts of heat through friction. This tidal heating produces more volcanic activity per unit area than any other body in the solar system, and keeps the interior partially molten. If you were deposited on Io in a relatively calm location, away from an active volcano, the first problem is still the atmosphere. Io has an extremely thin atmosphere of sulfur dioxide, at a pressure of about 1 to 10 nanopascals at the surface, far too thin to breathe, and essentially a vacuum for biological purposes. You would lose consciousness in 15 seconds from oxygen deprivation. However, Io adds a special killer that would begin acting immediately: radiation. Io orbits within Jupiter's powerful radiation belts, and the particle flux at Io's surface delivers doses of approximately 3,600 gray per day. A lethal whole-body dose for a human is about 6 gray. Io would deliver this lethal dose in approximately 1 minute and 24 seconds. The radiation would be causing cellular damage throughout your body from the first instant of arrival, breaking DNA strands, disrupting cellular chemistry, destroying the lining of blood vessels and the intestine. However, since the oxygen deprivation would render you unconscious in 15 seconds, you would not be aware of the radiation damage that was already occurring. If you were deposited near an active volcanic region, additional hazards would apply. Io's lava reaches temperatures of approximately 1,600 degrees Celsius, far higher than Earth's typical volcanic temperatures, and suggesting an unusually iron-rich or magnesium-rich mafic composition. Sulfur dioxide gases from volcanic plumes would be locally abundant. The ground itself in some regions is unstable volcanic material and hot sulfur deposits. The heat flux from Io's interior, while distributed globally, means that the average surface temperature is only about -143 degrees Celsius, with extreme variations. The sunlit side is warmer, around -95 degrees Celsius, and the shaded regions and poles are much colder. The volcanic regions themselves are dramatically hotter than average. Your survival time on Io: 15 seconds of consciousness from oxygen deprivation, then unconsciousness and death within minutes, while simultaneously receiving radiation doses that would cause radiation sickness in the first few minutes, even if oxygen were somehow available. The scale of Io's volcanic activity is difficult to overstate. The total heat flux from Io's interior is approximately 2.4 watts per square meter, about 40 times Earth's global average geothermal heat flux. This translates to a surface that is constantly resurfacing itself. Lava flows and pyroclastic deposits from eruptions cover the surface so rapidly that impact craters, which accumulate over time on almost all other solid bodies, are essentially absent on Io. The surface is so geologically young and so constantly renewed that it looks nothing like any other moon in the solar system. Some of Io's volcanic plumes are enormous. The Pele volcano produces a plume approximately 300 kilometers high, depositing a ring of sulfur compounds 1,400 kilometers across around the vent. The Tvashtar Paterae, imaged by the New Horizons spacecraft en route to Pluto in 2007, showed a plume approximately 330 kilometers high with a distinctive umbrella shape. These are among the tallest volcanic plumes in the solar system, driven by the superheated sulfur dioxide and other gases that can escape Io's low gravity. The composition of Io's surface changes continuously as different volcanic materials are deposited and chemically transformed by radiation. Sulfur compounds produce the characteristic yellows, oranges, and reds, while white areas are freshly deposited sulfur dioxide frost. Dark areas mark recent lava flows. The colorful, constantly changing surface of Io is the direct result of the same tidal forces that make it lethally radioactive. The gravitational flexing that heats the interior also drives the volcanism that covers the surface. Europa is Jupiter's second large moon, and possibly the most scientifically interesting object in the solar system from an astrobiological perspective. Beneath its frozen water, ice surface lies a global liquid water ocean, kept liquid by the same tidal heating that powers Io's volcanoes, though at more moderate levels. Europa's ocean is estimated to be 60 to 150 kilometers deep, potentially containing twice as much liquid water as all of Earth's oceans combined. This has made Europa a priority target in the search for life beyond Earth. But the surface of Europa is not the ocean. It is a frozen crust of water ice, approximately 15 to 25 kilometers thick. And standing on that surface is a death sentence from multiple directions simultaneously. The atmosphere of Europa is an extremely tenuous oxygen atmosphere, produced not by biological processes, but by radiation from Jupiter breaking apart water molecules in the surface ice and allowing some oxygen to remain. The surface pressure of this oxygen atmosphere is approximately 1/10,000,000th of Earth's atmospheric pressure, functionally a vacuum. Despite being composed of the right gas for breathing, it is far too thin to support respiration. The partial pressure of oxygen is nowhere near sufficient to sustain consciousness. The 15-second unconsciousness timeline applies. The radiation environment on Europa is somewhat less extreme than on Io, but still lethal at a rate far faster than Earth's radiation limits. Europa receives approximately 540 milligrays per day of radiation, meaning a lethal dose would be delivered in approximately 11 to 12 days. This would not be relevant given the more immediate problem of oxygen deprivation. The surface temperature of Europa averages about minus 160 degrees Celsius, with temperatures varying somewhat between the equatorial and polar regions. This is cold enough to cause almost instantaneous frostbite on any exposed skin and would kill you from hypothermia within minutes, though again, the oxygen deprivation takes precedence. The ice surface itself is covered with distinctive red-brown streaks and mottled terrain, caused by salts and organic material from the ocean below being brought to the surface through cracks and surface renewal processes. Europa's surface is geologically young by solar system standards, perhaps only 40 to 90 million years old, indicating active resurfacing from below. The ice also creates a practical problem that would not have time to matter, but is worth noting. Europa's surface is covered with rough ice formations called chaos terrain, which in some regions consists of sharp, irregular ice blocks, and in others, relatively smooth plains that are still crossed by ridges and fractures. Moving across this terrain would be extraordinarily difficult even in a suit. Your survival time on Europa: 15 seconds of consciousness, death within minutes, while the radiation dose accumulates but at a slower rate than on Io. The ocean beneath Europa's ice crust is estimated to be between 60 and 150 kilometers deep. For comparison, the maximum depth of Earth's oceans is about 11 kilometers at the Mariana Trench. Europa's ocean, if these estimates are correct, contains roughly twice the volume of all Earth's oceans. This is an enormous amount of liquid water, maintained in a liquid state not by solar energy, but by tidal heating, the same mechanism that powers Io's volcanoes, but at more moderate levels in Europa's case. The question of whether this ocean might harbor life is one of the most compelling in astrobiology. The key ingredients typically considered necessary for life, as we know it, are liquid water, chemical energy sources, and the organic building blocks of biology. Europa likely has all three. The liquid water is confirmed. The interaction between the ocean floor and the rocky mantle below likely produces hydrothermal vent systems similar to those on Earth's ocean floor, which provide chemical energy through the oxidation of hydrogen and sulfide compounds. And the radiation-processed surface chemistry produces oxidants that could, if they make their way into the ocean, provide additional energy sources for biological processes. The Europa Clipper mission, launched in October 2024, is designed to study Europa through a series of close flybys, measuring the ice thickness, characterizing the ocean's composition through plumes and other observable features, and assessing the habitability of the subsurface environment. It is not expected to drill through the ice or directly sample the ocean, but it will provide data that will guide decisions about future, more capable missions. Ganymede is Jupiter's largest moon, and the largest moon in the entire solar system, larger than the planet Mercury. It has a radius of about 2,634 kilometers and would easily qualify as a planet if it orbited the Sun directly. What makes Ganymede particularly interesting among the Galilean moons is that it is the only moon in the solar system known to have its own magnetic field, generated by an iron core, and this magnetic field creates a small magnetosphere embedded within Jupiter's larger magnetosphere. The magnetic field provides Ganymede with a degree of shielding from Jupiter's radiation belts that Io and Europa lack. The radiation dose at Ganymede's surface is estimated at approximately 8 milligrays per day, substantially lower than Europa's and vastly lower than Io's. This is still about 240 times Earth's average radiation dose and would be unhealthy for long-term habitation. But it represents a relatively more radiation-friendly environment among the Galilean moons. The atmosphere of Ganymede is comparable to Europa's in its extreme thinness. A tenuous oxygen atmosphere has been detected, generated by radiation processing of the icy surface, with a surface pressure of approximately 1/10,000,000th of Earth's. This oxygen is entirely insufficient for respiration, and the 15-second consciousness timeline from oxygen deprivation applies. Surface temperatures on Ganymede range from approximately -183 degrees Celsius in the polar ice caps to about -103 degrees Celsius in the warmer equatorial regions. The surface is a mixture of ancient, heavily cratered dark terrain and younger, less cratered bright grooved terrain, indicating a complex geological history. Like Europa, Ganymede is thought to have a subsurface ocean, though beneath a thicker ice crust than Europa's, and possibly between layers of different ice phases rather than in direct contact with a rocky seafloor. The surface gravity of Ganymede is about 0.146 g, roughly the same as the Moon. This low gravity combined with the vacuum conditions means that impacts from micrometeoroids, which continuously shower all airless bodies in the solar system, are a slow-acting hazard. Ganymede has been struck by these impacts over billions of years, creating the cratered landscape visible in spacecraft images. The invisible killer that the chapter title references is the combination of the oxygen atmosphere that looks breathable but isn't, and the radiation that is invisible but continuously damaging. On a world with an oxygen atmosphere, however thin, and a magnetosphere, however small, there is a superficial resemblance to conditions that might be survivable, but neither the atmospheric pressure nor the radiation shielding come close to what biological life requires. Your survival time on Ganymede, 15 seconds of consciousness, death within minutes from oxygen deprivation, with radiation delivering a lethal dose over approximately 750 days, long after the faster mechanisms have acted. The question of how Ganymede acquired its internal magnetic field is an important one for understanding planetary differentiation. Ganymede is thought to have differentiated early in its history, with heavy iron and nickel sinking to form a metallic core and lighter silicate materials forming the mantle and crust. The dynamo that generates the magnetic field requires a liquid iron outer core with convective motion, similar to what powers Earth's magnetic field. The fact that Ganymede's core is still partially liquid, allowing dynamo action after over 4 billion years of cooling, suggests either that the radioactive element content of Ganymede's interior provides ongoing heating, or that tidal forces from Jupiter and the other Galilean moons contribute to keeping the interior warmer than it would otherwise be. NASA's Juno spacecraft, primarily designed to study Jupiter's interior structure and magnetic field, has also been conducting close flybys of the Galilean moons in its extended mission. A June 2021 flyby of Ganymede passed within 1,038 kilometers of the surface, producing the closest images of Ganymede since Galileo in the early 2000s and revealing detailed surface features of both the dark and bright terrain types. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, launched in April 2023 and is en route to Jupiter, where it will eventually enter orbit around Ganymede specifically, becoming the first spacecraft to orbit a moon other than Earth's moon. JUICE is expected to arrive at Jupiter in 2031 and will characterize Ganymede's ocean, interior, and surface in detail. Saturn is the most visually iconic planet in the solar system. The ring system, extending tens of thousands of kilometers from the planet's equator, is the most striking visual feature in the entire solar neighborhood and has captured human imagination since Galileo first observed the planet through a telescope in 1610, although he was confused by what he saw, describing it as having ears. The beauty is a completely false signal about the habitability. Saturn shares Jupiter's fundamental problem of having no solid surface, only a continuous atmosphere that deepens and becomes denser and hotter as you descend into it. The composition is similar, approximately 96% hydrogen and 3% helium, with trace amounts of methane, ammonia, water vapor, and other compounds. No oxygen, no breathable air. The 15-second consciousness limit from oxygen deprivation applies the moment you arrive at the cloud tops. Saturn's cloud top gravity is about 10.44 meters per second squared, slightly greater than Earth's and significantly less than Jupiter's. You would fall through the cloud tops at roughly Earth-equivalent acceleration, rather than the 2.5 g acceleration on Jupiter. The fall into Saturn's atmosphere would be somewhat more leisurely than into Jupiter's, but would ultimately end in the same compressed, heated dissolution of biological tissues as the atmosphere deepens. Saturn's internal heat contributes significantly to its energy balance. Like Jupiter, Saturn radiates more energy than it receives from the Sun, generating about 2.5 times more heat than it absorbs from solar radiation. The internal heat is produced partly by the slow gravitational contraction of the planet and partly by the differentiation of helium, which is thought to be raining out of the outer hydrogen-helium mixture and sinking toward the core, releasing gravitational energy. This helium rain is also thought to be responsible for Saturn's lower helium abundance compared to Jupiter. Saturn's famous rings are composed primarily of water ice, with some rocky debris and dust, ranging in size from tiny grains to boulders several meters across. The ring particles are in stable orbits around Saturn, and would not be an immediate hazard to a person deposited near them, though the radiation environment near Saturn, while less extreme than near Jupiter, still delivers doses significantly above safe levels. The temperature at Saturn's cloud tops is approximately minus 178 degrees Celsius, among the coldest of the gas giant's cloud tops because Saturn is farther from the Sun. Below the cloud tops, temperatures increase with depth, just as on Jupiter. Saturn's rings are made of about 95% ice and are believed to be cosmically young, possibly having formed within the last 100 million years, perhaps from the disruption of a moon or the capture of a comet. They will eventually disperse, and Saturn will lose its most distinctive feature over the next 100 to 400 million years. Your survival time on Saturn: 15 seconds of consciousness from oxygen deprivation while falling through the cloud tops, then descent into the increasingly dense, hot, pressurized atmosphere. Saturn's ring system is made up of hundreds of thousands of individual ringlets and consists primarily of water ice particles with some rocky debris. The rings extend from about 7,000 kilometers above Saturn's equator to about 80,000 kilometers outward, but their thickness is remarkably small relative to their extent. Most of the main rings are only about 10 to 100 meters thick. The rings reflect sunlight efficiently because the water ice is fresh and bright. Over time, the rings are being slowly darkened by space weathering and contaminated by infalling meteoritic debris, contributing to the relatively young age of the current ring system. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided extraordinarily detailed information about the ring system, the planet's atmosphere, its magnetic field, and its moons. In the final phase of the mission, called the Grand Finale, Cassini made 22 orbits that passed between the innermost ring and the planet's cloud tops, a region that had never been explored. These final orbits provided direct measurements of Saturn's atmosphere and ring composition before the spacecraft was intentionally plunged into Saturn's atmosphere to prevent contamination of the moon systems. Cassini's entry into Saturn's atmosphere was itself a data collection opportunity, providing atmospheric measurements until communication was lost. Saturn's north polar region features a persistent hexagonal cloud pattern approximately 32,000 kilometers in diameter, a geometric feature that has been stable for decades and is thought to be produced by a specific pattern of atmospheric jet stream interactions. This hexagon is one of the solar system's most distinctive visible features and has no analog on any other known planet. Saturn's moon Titan is one of the most Earth-like environments in the solar system in certain superficial respects, and one of the most alien in others. Titan has a thick, opaque atmosphere with a surface pressure of approximately 1.5 times Earth's sea level atmospheric pressure, making it the only moon in the solar system with a substantial atmosphere and the only solar system body other than Earth with surface liquid in the form of stable lakes and seas. It has weather, erosion, river channels, dunes, and a complex organic chemistry that produces a perpetual orange haze. The atmosphere is composed primarily of nitrogen, about 95%, with approximately 5% methane and trace amounts of other hydrocarbons. The methane plays a role on Titan analogous to water on Earth. It evaporates, forms clouds, rains down, flows across the surface in rivers, and collects in lakes and seas. The Cassini spacecraft detected lakes and seas of liquid methane and ethane near Titan's poles, with the largest, Kraken Mare, being comparable in size to the Caspian Sea. If you were deposited on Titan's surface, the temperature would be approximately minus 179 degrees Celsius, nearly as cold as Saturn's cloud tops. Liquid methane, which has a boiling point of minus 161 degrees Celsius and a melting point of minus 182 degrees Celsius, exists as a liquid on Titan's surface. The lakes you see in imagery are not water, but liquid natural gas. A person standing on the shore of one of Titan's methane seas would be looking at a substance that, on Earth, is burned in stoves and furnaces. The atmosphere, while at a comfortable pressure, contains no oxygen whatsoever. Breathing Titan's atmosphere would be equivalent to breathing pure nitrogen. You would immediately begin to asphyxiate without any warning symptoms beyond the lack of oxygen, since carbon dioxide would not build up in your blood, rapidly enough to trigger the suffocation reflex before oxygen deprivation took hold. You would lose consciousness within 15 seconds. The cold at minus 179 degrees Celsius would cause almost instantaneous frostbite on any exposed skin and would rapidly kill you from hypothermia, but again, the oxygen deprivation is faster. However, Titan has an interesting distinction from the other worlds we have examined. You could survive the pressure. The 1.5 atmosphere pressure is well within human tolerance, and if you had somehow solved the temperature and atmospheric composition problems, Titan would be more mechanically survivable than any other world on this list outside Earth. Titan is also interesting because of the complex organic chemistry in its atmosphere. The Cassini probe detected hundreds of organic molecules in Titan's atmosphere, produced by ultraviolet radiation, and Saturn's magnetospheric particles breaking down nitrogen and methane and reassembling the atoms into more complex structures. Some of these molecules are the same types that are thought to have been important in the origin of life on early Earth. Your survival time on Titan: 15 seconds of consciousness from oxygen deprivation, then death from asphyxiation within minutes, with the cold simultaneously destroying exposed tissues. The Huygens probe, released by the Cassini spacecraft, descended through Titan's atmosphere in January 2005 and became the most distant probe landing in history. During its descent, it measured atmospheric temperature, pressure, and composition, and it transmitted images of the surface. The landing sequence took about 2.5 hours, during which Huygens transmitted data through Cassini. The probe continued transmitting from the surface for about 72 minutes after landing before its batteries were exhausted. The data it returned provided our first direct view of Titan's surface and confirmed the presence of a drainage network that had deposited material into the area where Huygens landed. The complex organic chemistry of Titan's atmosphere is generated when ultraviolet light and Saturn's magnetospheric particles break apart nitrogen and methane molecules, allowing the atoms to recombine into more complex organic molecules. This photochemical process creates a thick orange haze that gives Titan its distinctive color and reduces surface sunlight to about 1/1000th of what Earth receives from the sun. The same process produces tholins, complex organic molecules that accumulate on the surface as a reddish-brown material. NASA's Dragonfly mission, a rotorcraft lander approved for development, is planned to launch in the late 2020s and arrive at Titan in the 2030s. Dragonfly will use Titan's thick atmosphere and low gravity to fly between different surface locations, conducting chemical analyses at multiple sites to investigate the prebiotic chemistry and assess the potential for habitability in different environments on Titan's surface and in its subsurface. Enceladus is Saturn's sixth largest moon, with a diameter of only 504 kilometers, making it roughly the size of the state of Arizona. It is small enough that its surface gravity is only about 0.113 g, meaning you would weigh about 11% of your Earth weight on its surface. A typical adult could jump high enough to escape the moon's gravity with a sufficiently vigorous push, reaching escape velocity of about 239 meters per second with an appropriate angled jump, though this requires careful calculation and the right velocity vector. What makes Enceladus extraordinary, and what makes it one of the highest priority targets in the search for extraterrestrial life, is what is happening at its south pole. The Cassini spacecraft discovered that the south polar region of Enceladus has dozens of geysers erupting from a series of parallel fissures called tiger stripes, ejecting water vapor, ice particles, sodium salts, organic molecules, and molecular hydrogen into space at approximately 400 meters per second. The plumes create a virtual geyser that contributes material to Saturn's E-ring, which Enceladus orbits within. The presence of liquid water beneath the ice, detected through these plumes, makes Enceladus one of a select group of places in the solar system where conditions for life, as we know it, might exist. The plume material contains silica nanoparticles, indicating that the liquid water has been in contact with hot rocky material at the seafloor, creating conditions analogous to hydrothermal vents in Earth's oceans, which are among the most biologically productive environments on Earth, despite being completely disconnected from solar energy. If you were deposited on Enceladus's surface, you would face a near vacuum. The atmosphere of Enceladus is essentially none, a thin wisp of water vapor and other plume gases at pressures negligible compared to biological requirements. The 15-second oxygen deprivation scenario applies, but the situation has a unique feature. If you were deposited near the South Polar geysers, you would be showered with plume material that includes water ice particles and various organic and inorganic compounds, traveling at hundreds of meters per second. These particles would sandblast your skin with ice at 400 meters per second, though the damage from this would be secondary to the oxygen deprivation. Surface temperature on Enceladus varies from about -198 degrees Celsius in most areas to warmer regions near the Tiger Stripes at the South Pole, where internal heat raises temperatures to -93 degrees Celsius in the fissures themselves, still far below any habitable range. Your survival time on Enceladus: 15 seconds of consciousness from oxygen deprivation. Death within minutes, with the plumes adding a distinctive mechanical hazard if you are near the South Polar region. The discovery of Enceladus's plumes by the Cassini spacecraft in 2005 was one of the most significant planetary science discoveries of the 21st century. Scientists had expected Enceladus to be a cold, geologically dead world based on its small size. What Cassini found was a world with active water vapor plumes, thermal anomalies at the South Pole, and geological features indicating recent and ongoing activity. The revision required was substantial. Enceladus had somehow maintained enough internal heat to keep water liquid despite being only 504 kilometers across. The plume material sampled by Cassini contained not just water vapor and ice particles, but also sodium chloride, potassium salts, silica nanoparticles, carbon dioxide, methane, ammonia, and complex organic molecules, including simple amino acids and precursors. The presence of silica nanoparticles is particularly significant. These require water at high temperature, above 90 degrees Celsius, in contact with rocky material to form. This indicates that hydrothermal activity is occurring on Enceladus's seafloor, creating conditions analogous to Earth's hydrothermal vent systems. Molecular hydrogen detected in the plumes by Cassini in 2017 was another key finding. Molecular hydrogen is produced by the reaction of water with rock in hydrothermal systems, and it provides a potential energy source for chemolithotrophic life, organisms that derive energy from chemical reactions involving hydrogen. On Earth, these types of organisms thrive around hydrothermal vents deep in the ocean, far from sunlight. The detection of hydrogen in Enceladus's plumes means that a similar energy source is available in its ocean, strengthening the case that Enceladus has the necessary conditions to support life. The implications of Enceladus's habitability are profound because of how accessible the ocean is. Whereas accessing Europa's ocean would require drilling through 15 to 25 kilometers of ice, Enceladus's ocean is essentially broadcasting its contents directly into space through the geysers. A spacecraft flying through the plumes can directly sample the ocean chemistry without needing to land or drill. The Cassini spacecraft made exactly these measurements, and a future dedicated Enceladus mission could carry even more sensitive instruments to characterize the ocean's chemical environment in detail, and potentially detect biosignatures if any exist. Uranus is an ice giant with an axial tilt of approximately 97.77 degrees, meaning it rotates essentially on its side relative to its orbital plane. This extreme tilt means that Uranus's poles receive more sunlight than its equator over the course of its 84-year orbit, and each pole spends about 42 years in continuous sunlight and 42 years in continuous darkness. This creates the most extreme seasonal variation of any planet in the solar system, though the low solar energy at Uranus's distance from the Sun means the temperature differences are modest. Uranus is composed primarily of water, methane, and ammonia ices surrounding a small rocky core, with an outer atmosphere of hydrogen and helium. The bluish-green color of Uranus, somewhat distinct from Neptune's deeper blue, is caused by methane in the upper atmosphere absorbing red light. Uranus's atmosphere contains approximately 83% hydrogen, 15% helium, and about 2.3% methane. If you were deposited at Uranus's cloud tops, the story is familiar. No oxygen, 15 seconds to unconsciousness, then a falling death into an increasingly dense and hot atmosphere below. The cloud top temperature of Uranus is approximately minus 224 degrees Celsius, the coldest cloud top temperature of any planet in the solar system, despite Uranus being closer to the Sun than Neptune. Uranus emits almost no internal heat, unlike the other giant planets. The reason for this is not well understood, and is one of Uranus's distinctive mysteries. It may have been struck by a large body early in solar system history that disrupted its internal heat structure. The lack of internal heat output makes Uranus distinctly bland compared to the other gas giants. Neptune has enormous storm systems and wind speeds, driven partly by internal heat. Uranus has relatively featureless cloud layers and sluggish atmospheric dynamics by comparison. Voyager 2's 1986 flyby of Uranus found a surprisingly quiet atmosphere with few visible features, though subsequent observations from Earth have revealed more storm activity as Uranus's seasons have changed. Uranus has 27 known moons and a faint ring system discovered in 1977. The rings are narrow and dark, very different from Saturn's bright, broad ring system, and are maintained by shepherd moons that constrain the ring particles. The odd orientation of Uranus creates a genuinely alien day-night cycle and seasonal pattern. Standing at the North Pole during the polar summer, you would see the Sun circling continuously near the zenith for decades. Standing at the equator, you would experience relatively normal day-night cycles during Uranian spring and autumn, but extreme variations at solstice. But, of course, none of this is relevant for our scenario. You would be dead within minutes of arriving. Your survival time on Uranus: 15 seconds of consciousness from oxygen deprivation while falling into the atmosphere, then death within minutes, in the coldest cloud-top environment of any planet. The cause of Uranus's unusual axial tilt remains uncertain. The most widely accepted hypothesis is that a large body, roughly Earth-sized or larger, struck Uranus early in the solar system's history and knocked it onto its side. This kind of giant impact would also explain some other unusual features of Uranus, including the fact that its moons and rings are also tilted with the planet and orbit in the equatorial plane, consistent with a catastrophic early event that reset the entire system's angular momentum. One consequence of this extreme tilt that is worth appreciating is what it means for the poles. During Uranus's summer solstice, the pole that is facing the Sun receives continuous sunlight for 42 years. That same pole then faces away from the Sun for the next 42 years of polar winter. The equatorial regions experience a relatively normal day-night cycle during Uranus's spring and autumn, but extreme seasonal variation as the planet approaches and retreats from solstice. No planet in the solar system has a more extreme seasonal cycle. The methane in Uranus's upper atmosphere absorbs red light from the Sun, leaving the reflected light with a blue-green hue. This is the same mechanism that gives Neptune its deeper blue color, though Neptune's additional internal heat drives more vigorous atmospheric circulation that produces a somewhat different appearance. The absence of significant internal heat in Uranus results in the most stratified and least convective atmosphere of the giant planets, contributing to the relatively bland and featureless appearance that surprised scientists during the Voyager 2 flyby. Neptune is the outermost planet, and in some respects, the most violently active of the gas giants despite being the farthest from the Sun and receiving the least solar energy. Like Saturn and Jupiter, it radiates significantly more energy than it receives from the Sun, with an internal heat output about 2.6 times its solar input. This internal energy drives atmospheric dynamics that produce the fastest sustained winds in the solar system, reaching approximately 2,100 kilometers per hour in Neptune's equatorial regions. To put this in perspective, the fastest wind ever recorded on Earth was approximately 372 kilometers per hour during Tropical Cyclone Olivia in 1996. Neptune's winds are nearly 6 times that. The trade winds in Earth's tropics are perhaps 20 to 30 kilometers per hour. Neptune's winds exceed this by a factor of nearly 100. These are not occasional gusts, but sustained atmospheric jet streams that encircle the planet continuously. If you were deposited at Neptune's cloud tops, you would immediately be subjected to winds of approximately 500 to 2,100 kilometers per hour, depending on latitude, in an atmosphere of hydrogen and helium with no oxygen at a temperature of approximately minus 214 degrees Celsius. You would be struck by wind-driven cloud particles traveling at hurricane to supersonic speeds, asphyxiating from lack of oxygen, and freezing from the cold, all simultaneously. The oxygen deprivation would be the fastest acting at 15 seconds to unconsciousness, as on every other gas or vacuum world we have examined. However, the winds would be the most dramatically visceral of the killing mechanisms. A person standing in 2,100 km per hour wind, if such a thing were possible, would be literally thrown and tumbled at extreme speed. At those velocities, the dynamic pressure of the atmospheric gas, thin as it is at cloud top level, would still be sufficient to cause serious physical injury from aerodynamic forces. Neptune's most famous atmospheric feature is the Great Dark Spot, observed by Voyager 2 in 1989, a storm system roughly the size of Earth. Unlike Jupiter's Great Red Spot, which has persisted for at least centuries, Neptune's Great Dark Spot had disappeared when Hubble Space Telescope observed Neptune in 1994, replaced by new storm features elsewhere. This indicates that Neptune's atmosphere, despite its extreme wind speeds, produces storm systems that are dynamic and transient rather than stable, long-lived features. Neptune has only been visited once, by Voyager 2 in 1989, which is the only spacecraft to have flown past Uranus and Neptune. No mission is currently confirmed to return to either ice giant, though both are high priorities for future planetary exploration. Your survival time on Neptune: 15 seconds of consciousness from oxygen deprivation, while simultaneously being subjected to winds that exceed the fastest hurricanes on Earth by a factor of 6. The Great Dark Spot observed by Voyager 2 in 1989 was a storm system roughly the size of Earth, featuring wind speeds at its edges of about 2,400 kilometers per hour. Its disappearance by 1994, when Hubble Space Telescope began observing, Neptune demonstrated that unlike Jupiter's Great Red Spot, which has been stable for centuries, Neptune's major storm systems can dissipate on human timescales. New storm systems have appeared and disappeared in subsequent Hubble observations, suggesting that Neptune's atmosphere is in a state of continuous dynamic evolution, driven by its powerful internal heat source. The source of this internal heat, as mentioned earlier, is not fully understood. The heat must be generated by some process occurring in Neptune's interior, Either the slow gravitational contraction of the planet, the differentiation of denser materials toward the core, or possibly some form of latent heat release from phase transitions in the interior's exotic high-pressure physics. Whatever its source, this internal energy is responsible for Neptune having far more active weather than Uranus, despite being smaller, farther from the Sun, and colder at the cloud tops. Neptune's largest moon, Triton, orbits in the retrograde direction at an inclination of about 157 degrees to Neptune's equatorial plane, confirming its captured Kuiper Belt origin. Triton's presence has likely destabilized any original prograde moons that Neptune formed with, and Neptune's current collection of smaller moons are thought to be the remnants of the collisional debris from Triton's capture event. Triton's retrograde orbit is slowly decaying due to tidal interactions with Neptune, eventually dooming Triton to tidal disruption in billions of years. Triton is Neptune's largest moon and one of the most unusual objects in the solar system. It orbits Neptune in the opposite direction from Neptune's rotation, a retrograde orbit that indicates it was captured from the Kuiper Belt rather than forming in place around Neptune. Like all captured moons, Triton's initial highly elliptical orbit was gradually circularized by tidal interactions with Neptune, and the tidal heating from this process may have melted the interior of Triton completely sometime in the past. At 2,706 kilometers in diameter, Triton is the seventh largest moon in the solar system. It orbits very close to Neptune at only 354,759 kilometers, closer than the Moon is to Earth, and it is slowly spiraling inward due to tidal interactions. In approximately 3.6 billion years, Triton will cross within Neptune's Roche limit and be torn apart by tidal forces, potentially creating a new ring system around Neptune. The surface temperature of Triton is approximately minus 235 degrees Celsius, making it the coldest measured surface of any object in the solar system. This temperature is only 38 degrees above absolute zero. At this temperature, nitrogen is solid, covering the surface in a layer of frozen nitrogen ice. The south polar region shows a distinctive pinkish tint from organic compounds produced by radiation processing of methane ice. Triton's atmosphere is extremely thin, primarily nitrogen with trace amounts of carbon monoxide and methane, at a surface pressure of about 14 microbars, approximately 0.00001% of Earth's atmospheric pressure. This is a vacuum for biological purposes, and the oxygen deprivation timeline of 15 seconds applies. The remarkable thing about Triton is that despite its extreme cold, it is geologically active. Voyager 2 observed nitrogen geysers erupting from the south polar region, driven by sunlight penetrating the transparent nitrogen ice and heating the dark material beneath. The geysers eject nitrogen gas and dark particles several kilometers into the atmosphere, on a world where the surface temperature is minus 235 degrees Celsius. These geysers are evidence that even minimal solar energy input can drive geological processes at the right conditions. The retrograde orbit and Kuiper Belt origin of Triton make it a window into the distant outer solar system. Its composition and structure are likely similar to Pluto and other large Kuiper Belt objects, providing a local example of what the distant trans-Neptunian population looks like up close. Your survival time on Triton: 15 seconds of consciousness in the near vacuum, then death within minutes at the coldest natural surface temperature in the solar system. Triton's nitrogen geysers are powered by a mechanism that illustrates how creative solar system physics can be in generating geological activity from minimal energy input. Sunlight at Neptune's distance is about 900 times weaker than at Earth's distance, but the transparent nitrogen ice is unusually good at allowing this weak sunlight to penetrate and heat the darker subsurface material beneath. The dark material heats up above the sublimation temperature of nitrogen, creating pressurized nitrogen gas that eventually breaks through the overlying ice. The result is a geyser that can reach heights of 8 kilometers and transport dark material downwind by hundreds of kilometers. The Voyager 2 flyby of Triton in August 1989 provided our only close-up view of this moon and all its features. The spacecraft flew within 40,000 kilometers of Triton's surface, close enough to image features down to about 2 kilometers in size. The images revealed a surprisingly diverse surface with pink nitrogen ice caps, older cratered terrain in the northern hemisphere, and younger, geologically complex terrain in the southern hemisphere, including the Cantaloupe terrain. A distinctive pattern of irregular, shallow depressions, with no clear analog on other solar system bodies. The composition of Triton's surface includes nitrogen ice, methane ice, carbon dioxide ice, and carbon monoxide ice, as well as the dark reddish-brown tholin material common to outer solar system bodies exposed to radiation processing. The combination of ice types at the surface reflects the complex thermal and chemical history of a body that was captured from the Kuiper Belt and subsequently reprocessed by tidal heating and radiation. Pluto orbits the Sun at an average distance of about 5.9 billion kilometers, nearly 40 times the Earth-Sun distance. It is the largest known Kuiper Belt object, and the object most people still think of as the 9th planet, though it was reclassified as a dwarf planet in 2006 when the International Astronomical Union formally defined what a planet is. The reclassification remains contentious, but reflects the fact that Pluto is one of hundreds of similar objects in the Kuiper Belt, rather than a unique planetary body. The New Horizons spacecraft flew past Pluto in July 2015, providing the first close-up images of this distant world. The images revealed a world of unexpected geological complexity. Vast plains of nitrogen ice in the heart-shaped Tomball Regio, mountain ranges of water ice rising 3,000 meters above the plains, evidence of geological processes including possible cryovolcanism, and a surprisingly varied landscape for a world at the edge of the solar system. The surface temperature of Pluto averages about minus 225 to minus 233 degrees Celsius, depending on location and season. Pluto's highly elliptical orbit takes it from 29 to 49 astronomical units from the Sun, and the eccentric orbit combined with the extreme distance creates the most extreme variation in solar energy input of any significant solar system body. At perihelion, Pluto receives slightly more solar energy, and its thin atmosphere becomes more active. Pluto's atmosphere is composed primarily of nitrogen, with trace amounts of methane and carbon monoxide, at a surface pressure of approximately 1 to 25 microbars, depending on the season and Pluto's distance from the Sun. This is still functionally a vacuum, completely insufficient for respiration. The 15-second oxygen deprivation timeline applies. The combination of extreme cold and near vacuum on Pluto would simultaneously produce frostbite, hypothermia, and ebulism on a time scale measured in seconds to minutes. The near vacuum is the fastest acting killer, but at minus 230 degrees Celsius, the cold would destroy tissue with extraordinary speed. Any exposed skin would freeze so quickly that it would be difficult to distinguish from the other mechanisms of destruction. Pluto's moons are an interesting system. Charon, the largest, is so large relative to Pluto that some consider the pair to be a double dwarf planet. Charon's diameter is about 51% of Pluto's, and the two orbit a common barycenter that lies in the space between them, rather than within Pluto's body. 4 much smaller moons, Styx, Nix, Kerberos, and Hydra, orbit in the outer system. Your survival time on Pluto: 15 seconds of consciousness, death within minutes from oxygen deprivation, in the second coldest natural surface environment in the solar system after Triton. The heart-shaped feature on Pluto, named Tomball Regio after Clyde Tombaugh, who discovered Pluto in 1930, consists of a vast nitrogen ice plain in its western lobe and a mixture of different terrains in its eastern lobe. The nitrogen ice plain, informally named Sputnik Planitia, is about 1,000 kilometers across and sits in what may be an ancient impact basin. The nitrogen ice flows slowly, driven by the slight temperature differences between its surface and interior, creating patterns of convection cells visible as polygonal features in images. This makes Sputnik Planitia a site of active geological process, with the slow creep of nitrogen ice redistributing material across the surface. Pluto's interaction with the solar wind is distinctive because Pluto lacks a significant magnetic field. The solar wind interacts directly with Pluto's atmosphere, stripping material away over time. The New Horizons mission detected a comet-like tail of atmospheric material being carried away from Pluto by the solar wind, trailing millions of kilometers behind the dwarf planet. This erosion has been ongoing throughout Pluto's history and may have significantly reduced the total atmospheric mass over billions of years. The discovery of the Pluto system's complexity by New Horizons changed the way planetary scientists think about small body systems. Before the flyby, Pluto was largely imagined as a featureless, static world at the edge of the solar system. What New Horizons found was a world of mountains and plains, varied terrain, active atmospheric processes, and a large moon with its own interesting geology. The lesson was that geological activity can persist in small bodies with the right conditions, even far from the sun. Every killing mechanism we have discussed in this tour, the heat of Venus, the cold of Triton, the radiation of Io, the crushing pressure of the gas giants, all ultimately traces its origin back to one source: the sun. The sun is responsible for the temperature structure of the solar system, for the radiation that bombards the inner planets and the moons of Jupiter, for the solar wind that strips away thin atmospheres, and for the thermal energy that drives atmospheric circulation on planets that have it. But the sun itself is by far the most immediately lethal object in the solar system, and examining what would happen to a human placed on or near the sun is a useful capstone to the entire tour. The sun is a ball of plasma with no solid surface. The visible surface we see from Earth, the photosphere, is not a true surface but a layer of plasma from which light can escape freely. The temperature of the photosphere is approximately 5,500 degrees Celsius. The corona, the sun's outer atmosphere, which is visible during solar eclipses as the pearly white halo surrounding the sun, is paradoxically much hotter, reaching temperatures of 1 to 3 million degrees Celsius. The reason the corona is hotter than the photosphere below it, despite being farther from the nuclear energy source in the core, is one of the outstanding problems in solar physics. If you were deposited on the photosphere, you would be vaporized instantaneously. At 5,500 degrees, Celsius matter does not exist as solid or liquid or even as ordinary gas. The atoms themselves would be stripped of their electrons, becoming the plasma that the sun consists of. Your constituent atoms, the carbon and hydrogen and nitrogen and other elements that make up your body, would be dissociated from any molecular form and would exist as individual ions and electrons within the solar plasma. The timescale here is not 15 seconds or even 1 second. The timescale is nanoseconds. The thermal radiation alone, without any need to touch the solar surface, would deliver an energy flux at the solar surface of about 62.6 megawatts per square meter. Your body surface area is roughly 1.7 to 2 square meters. You would be receiving approximately 100 to 125 megawatts of thermal energy. The fastest mechanisms of thermal destruction would operate on timescales measured in microseconds. Even in the corona, at 1 million degrees, you would be vaporized almost instantaneously, though the density of the corona is so low that the actual energy transfer per unit time would be less than at the photosphere despite the higher temperature. the sun's nuclear core, where hydrogen fusion produces the sun's energy, operates at about 15 million degrees Celsius. There, you would not merely vaporize, you would undergo nuclear reactions. Your constituent atoms would participate in the same fusion processes that power the sun, eventually contributing to the helium that the sun produces at roughly 600 million tons per second. Your survival time on the sun, nanoseconds to microseconds. There is no meaningful survival time. The structure of the sun provides context for understanding why its surface temperature is what it is, and why the corona is paradoxically much hotter. The nuclear fusion reactions that power the sun occur in the core, where temperatures reach 15 million degrees Celsius. Energy generated in the core takes approximately 100,000 years to reach the surface through a process of radiation and convection. Photons are produced in the core, but are absorbed and re-emitted so many times by the dense solar plasma that the journey to the surface is an extraordinarily slow, random walk. The photons that eventually escape as sunlight have been in transit for longer than our species has existed. The solar corona's extreme temperature is not directly connected to the nuclear energy of the core. Instead, it appears to be heated by wave energy transmitted from the churning surface through the magnetic field, similar to how waves on a rope can transmit energy from one end to the other. Alfvén waves, named after the Swedish physicist Hannes Alfvén, propagate along magnetic field lines and appear to deposit energy in the corona. This remains an active area of research, with the Parker Solar Probe mission specifically designed to study the mechanisms of solar wind acceleration and coronal heating by flying closer to the sun than any previous spacecraft. The sun loses approximately 600 million tons of hydrogen per second to the helium produced by fusion. Over its 4.6 billion year history, the sun has converted roughly 100 Earth masses of hydrogen to helium in its core. The sun has enough hydrogen remaining to continue fusing for approximately another 5 billion years, after which it will exhaust the hydrogen in its core and begin expanding into a red giant, eventually engulfing Mercury and Venus, and possibly Earth. Having toured every major world in the solar system, and examine the specific mechanisms that would end an unprotected human life on each one, it is worth stepping back and organizing what we have found into a coherent picture. The killing mechanisms form a hierarchy, and understanding that hierarchy illuminates something important about the solar system's structure and about what makes Earth so exceptional. The fastest killing mechanism in the solar system is extreme high temperature. Venus and the Sun represent the extreme end of this spectrum, with Venus killing within fractions of a second and the Sun within nanoseconds. Venus's 465 degrees Celsius surface temperature, combined with 92 atmospheres of pressure, creates a lethal environment where every biological process fails simultaneously and instantly. The Sun's photosphere destroys the very concept of molecular biology within microseconds. The second tier of lethality involves radiation. Io delivers lethal radiation doses in approximately 84 seconds, making it one of the few places in the solar system where death by a mechanism other than oxygen deprivation or heat is the primary concern. The radiation comes from Jupiter's trapped charged particles in its radiation belts, and Io's position within those belts creates a radiation environment that is among the most intense on any solid surface in the solar system. The third tier, which covers the majority of solid surfaces we examined, is oxygen deprivation in near-vacuum environments. The Moon, Mercury, Mars, Ceres, Europa, Ganymede, Enceladus, Triton, and Pluto all deliver death within the same 15-second to 4-minute window from the same cause. Their atmospheres are too thin to provide the oxygen partial pressure required for respiration. Some of these worlds have no atmosphere at all. Others have tenuous atmospheres of the wrong gases. The result is the same: The cold is an important secondary killer on many worlds, but rarely acts faster than oxygen deprivation on solid bodies. The exception would be very slow deposition of a person who for some reason managed to maintain air supply, but lacked insulation on Triton at -235 degrees Celsius, where the thermal destruction would proceed rapidly. The gas giants kill through falling and compression in an atmosphere that becomes progressively denser, hotter, and more pressurized as depth increases. You never hit a surface because there is no surface. You simply fall and are gradually converted from a person into a dispersed mixture of organic molecules, and then into individual atoms as depth and temperature increase. Titan is a special case. It has the right atmospheric pressure for human survival, but the wrong atmospheric composition and the wrong temperature. If those two problems were solved, Titan would be the most habitable non-Earth environment in the solar system based on pressure alone. The single overwhelming conclusion from this entire tour is that Earth is extraordinary. Not merely comfortable, not merely adequate, but extraordinarily, improbably, precisely configured for human life in ways that no other world in the solar system comes close to matching. The pattern of survival times across the solar system has a geographic logic to it that is worth making explicit. The very inner solar system, especially Venus, is dominated by heat death. The outer solid worlds, from the Moon outward through Pluto and Triton, are dominated by vacuum and cold. The gas giant cloud tops kill through atmospheric asphyxiation while allowing you to fall. The energetically active Moon, Io, kills through radiation faster than the surrounding vacuum would on any other airless world. And the Sun is in a category entirely its own. The intermediate zone, Mars, is interesting because it represents the transition between worlds where heat is the primary problem and worlds where cold and vacuum dominate. Mars is cold, and its atmosphere is too thin to breathe, but these problems have the same solution in principle, namely, provide heat and provide breathable air at sufficient pressure. The engineering of a Mars habitat is challenging, but not fundamentally different from engineering an Antarctic research station or a submarine. The challenge is the scale and the remoteness. The comparison between different killing mechanisms also reveals something about what resources would be needed to make different environments survivable with technology. Venus's problems are harder to solve than Mars's. You would need not just breathable air and heat management, but also protection from crushing pressure and corrosive chemistry. Jupiter requires you to create an environment in a gas that has no surface, which is a fundamentally different engineering challenge from simply pressurizing a structure on a solid surface. The hierarchy of hostility maps roughly onto the hierarchy of engineering difficulty for future human presence. There is a specific kind of appreciation for Earth that only becomes accessible through this exercise. When you have spent time genuinely examining what each of the other worlds in the solar system would do to you, and how quickly, the taken-for-granted character of Earth's conditions becomes impossible to maintain. The atmosphere you are breathing right now has exactly the right composition. The partial pressure of oxygen at your current altitude is precisely within the range that your blood can absorb efficiently. The atmospheric pressure around your body is exactly in the range where your lungs can expand and contract naturally, where gas exchange at the alveolar surface operates effectively, where your cardiovascular system can function without the stresses of either vacuum or extreme compression. These conditions are not the norm in the solar system. They are the extreme exception. The temperature in most inhabited regions of Earth falls within a range of perhaps -50 to +50 degrees Celsius, and the average inhabited temperature is far narrower than that. This is a range within which water is liquid, within which enzyme kinetics operate at biological rates, within which the organic chemistry of life can function. Every other world we examined in detail either cannot support liquid water on its surface, or does so only in an underground ocean beneath an ice shell. Earth has a magnetic field that deflects the solar wind, and prevents the slow erosion of the atmosphere by energetic charged particles. Without the magnetic field, Earth's atmosphere would be gradually stripped away, as appears to have happened to Mars. The magnetic field is the invisible shield that makes the surface radiation environment safe for biological life. Earth has plate tectonics, which recycles carbon from the atmosphere into rocks and back again through volcanic outgassing, maintaining the carbon dioxide concentration at levels that provide greenhouse warming without the runaway effect that transformed Venus from a potentially habitable world into a furnace. The balance of the carbon cycle, regulated by the geological activity that most planets lack, is responsible for Earth's stable temperature over billions of years. Earth has a large moon that stabilizes its axial tilt, preventing the kind of extreme wobbling that might create uninhabitable climate swings over millions of years. The moon's influence on Earth's tides has also been proposed as a factor in the evolution of early life. The synthesis of all this is that Earth works as a habitat for complex life because of an intersection of multiple independent favorable conditions that reinforce each other. Remove the magnetic field and the atmosphere erodes. Remove the plate tectonics and the carbon cycle regulation breaks down. Remove the right distance from the sun and the temperature falls outside the range for liquid water. The survival times on the other worlds in the solar system are the negative space that defines the positive space of Earth's habitability. The exercise of asking how long you would last on other worlds is ultimately an exercise in answering the question, what makes Earth the only world in the solar system where you can simply exist, unprotected, for an entire lifetime? The answer is everything. Every major physical property of Earth, its distance from the sun, its atmospheric composition, its surface pressure, its magnetic field, its tectonic activity, its large stabilizing moon, its water cycle, all of these must be simultaneously correct for a human life to simply begin and persist. The other worlds of the solar system are not just hostile environments. They are, each in their own way, demonstrations of how many things can go wrong and how lethal each wrongness is. Understanding their hostility is the most direct path to understanding Earth's extraordinary, improbable, and fragile rightness. The famous pale blue dot image taken by Voyager 1 in 1990 at Carl Sagan's request from a distance of approximately 6 billion kilometers shows Earth as a tiny fraction of a pixel suspended in a sunbeam against the darkness of space. Sagan's accompanying remarks about Earth being a mote of dust suspended in a sunbeam, our only home in the vast indifference of the cosmos, take on additional meaning once you have walked through in detail what every other visible location in that cosmos would do to you within seconds to minutes. The tour we have conducted is in some sense a guided meditation on contingency. Every feature of Earth that protects human life is contingent. It could have been otherwise, and in most places in the solar system, it is otherwise. The orbit at the right distance from the sun is contingent. The atmosphere with the right composition is contingent. The magnetic field that protects the atmosphere is contingent. The tectonic activity that regulates the carbon cycle is contingent. The large moon that stabilizes the axial tilt is contingent. Remove any one of these, and the others may not be enough. This contingency is not a reason for despair, but for attention. We exist in the one place in the solar system where existence is easy enough to be taken for granted, and we have constructed a civilization so insulated from direct experience of the physical world that the astonishing improbability of our survival conditions has become invisible. Every breath is possible only because of a confluence of physical factors so specific and so precisely balanced that nowhere else in our entire solar neighborhood can they be found. That is worth knowing. It is worth feeling. And it is the most important thing that a tour of the hostile solar system teaches.